Welcome back, my dear friends. A very good morning, good afternoon and good evening to all of you. This is the TQM2 lecture series under the NPTEL MOOC, and I am Raghunandan Sengupta from IME department, IIT Kanpur. So, we are in the penultimate stage of this TQM2 lecture series, and we have 2 lectures left, which is the 39th and the 40th. In the 39th, I will try to cover more topics, and 40th, I will try to basically wrap it up. I will discuss what are the things we should lay more stress on in the 40th lecture. So, let us continue the discussion. So, if you remember, we were discussing that given a multiple linear regression, a linear one, and which I keep saying time and again, our main hypothesis was basically to have them in a very simple linear format, find out the beta hats, and they should be unbiased, then try to find out generally the plot of the errors with respect to all the x's. X's are the independent variable. Then have the QQ plots to find out the distribution for the errors, or it can be done for the x's, y's, because intrinsically we are considering they are all normal. Then try to have a look at the covariance matrix or betas, and then we went into how, if there are utilizing the concept of the regression with the fractional factorial models, combining them like 2 to the power k, 3 to the power k. So, k is the number of variables, or it can be attributes also. So, you can have a regression where some of the x's are discrete, some of the x's are continuous. Then we consider that if they are orthogonals, how they can be done, then the not orthogonal, how the regression models can be done, and you can find out the beta hats. Then we also consider that if the folds can be done, folding and trying to find out what is the overall relationship between the x's and the y's. Then we went into basically testing whether the linearity holds. At the fag end of the last lecture, which is the 30th lecture, we considered that if all the betas are 0, that means there is no linear relationship between y and x, because if beta 1 is 0, it means the rate of change of y with respect to x 1 is not there, it does not exist. So, that means there is no dependence, and then we will consider the further on discussion from now on. But in all these things which I did mention is that at the end of the day, your main focus is to basically have a table of the ANOVA, which is analysis of variance, where in the first column I am again repeating, it will be all the variables and the attributes, and the second column it will be the sum of the squares. Then in the third column it will be degrees of freedom, fourth column it will be the mean square, that means the sum of the squares divided by the degrees of freedom. Then using the ratios of the mean squares or the ratios of the sum of the squares divided by the degrees of freedom will give you the F statistics, and you will basically have a value of alpha, level of confidence, or considering the p value, you will comment whether your hypothesis null is validated or not. And then we would basically consider as things are in the subsequent lecture which we are going to cover today. Now, if H naught, which is the null hypothesis beta j is 0, is not rejected, which means there is some linear relationship, then this indicates that x j can be deleted from the model. So, if it is not rejected, we will consider not consider depending on what our actual hypothesis is. The test statistic for the hypothesis would be the t value. So, this t value or the t statistics would be beta hat j, because beta hat j is basically the estimated value of beta, and divided by sigma square hat c j j. So, c j j are the diagonals of the x transpose x inverse matrix. So, that was one part when you are trying to find out the beta hats. So, beta hats would basically be found out such that in the long term the expected value of the beta hats are exactly equal to the beta. So, that is basically the characteristics of unbiasedness. The t statistics under H naught would be beta hat j divided by square root of sigma square hat and c j j. So, they would be the corresponding columns of the principal diagonal of that, because it is CJJ, it will be the values accordingly. The null hypothesis is H naught is basically if beta naught is j, it will be rejected if the value of both, because null hypothesis can be you are taking both sided. So, if it is both sided, obviously it will be either onto the left or the right, depending on which way you are looking at. The word what I am saying is that which way you are looking at is that whether the value of beta naught is equal to 0 or within the band range, considering the interval estimation, it is plus or minus. That means, plus some delta value with right of 0 and minus some delta value on the left of 0, if you are basically drawing the number line where 0 is the value where the null hypothesis basically is validated. Now, one should remember this concept of beta naught being equal to 0 can be changed as beta naught is equal to, say for example, some fixed value where we consider the linearity relationship between the x's or xj's and the y's are constant, and in another case a null hypothesis we can consider it is changing. So, that means, consider that under H naught beta j is, say for example, 3. So, that means, the rate of change of y with respect to beta with x, that corresponding x is 3 units, which is the regression coefficient, and under the null hypothesis it is 3, and under the alternative hypothesis not equal to 3. Then also the interval estimation would be done accordingly, where it will be 3 plus some delta, 3 minus some delta. You will basically consider that hypothesis is satisfied, outside this interval it is not satisfied. Now, this interval plus delta and minus delta which I am mentioning would depend on the level of confidence and the distribution you are taking. So, it will be T distribution with corresponding values being there. What are those values? I am going to come to that. So, the null hypothesis beta naught is equal to beta j under the null hypothesis being rejected would be true if this is true, that means it is greater. So, now check here what I did mention the right and left hand. So, I will just change the color. So, this alpha by 2 basically means the level of confidence. So, if you have, I am just drawing the distribution very simply, it is not normal, it is basically considered as a T distribution. So, these are the intervals, these values should be equal to alpha by 2, this value equal to alpha by 2, and the region in between this color or this region would basically be equal to alpha. Hence, this 1 minus alpha, sorry, my mistake, 1 minus alpha. So, 1 minus alpha plus alpha by 2 plus alpha by 2, the total area is 1, as it should be. And finally, this n minus k minus 1 is basically the degrees of freedom depending on the experiment we are doing. So, n is the total number of observations, k if you remember is the number of variables depending on which y can be estimated, and minus 1 is basically you are losing the degrees of freedom for that as 1. Note that this is really a partial and marginal test, because the regression coefficient beta j depends on all the other regression coefficients, which is true, because beta j would depend on beta naught, beta 1, beta 2, beta 3 till beta j minus 1, then beta j plus 1, beta j plus 2, so on and so forth till beta k. On other regression coefficients, I should basically mention not depend on beta naught till beta j minus 1 and beta j plus 1 till beta k. I am saying they should depend on the x values. So, x 1 to x j minus 1, then x j plus 1 till, say for example, x k. So, let me continue reading it. So, the regression coefficient beta j depends on all the other regression variables x I is not equal to j that are in the model considered. The denominator of this equation, which is the square root of sigma hat square c j j, is called the standard error of the regression coefficient beta j, because it is basically you are trying to multiply the variance with the multiplying factor. So, the standard error, so SE is the standard error. I will repeat, I have mentioned it very clearly in the last class, and also I faintly remember I did mention in the 37th class also. So, basically it means that standard error is the standard deviation of the sample So, which is the counterpart of the standard deviation which you have from the population, its counterpart in the sample is basically standard error. So, let me continue reading it. Standard error for beta j is equal to square root of sigma square hat C j j. Therefore, an equivalent way to write this test statistics would be as given, T naught is equal to beta j hat obviously, and divided by the standard error of beta j hat. So, obviously, you are trying to normalize it and find out the test statistics. Now, consider the model as given. So, you have basically y is equal to, so there is no beta naught. So, is equal to beta 1 x 1 plus beta 2 x 2 and plus epsilon. Now, the word which I mentioned, there is no beta naught. Technically, see the equation, they are all bolds. Bolds means there are matrices. So, let me, if I read it, it will become clear to you, where x I represents the columns of x associated with beta I. So, basically, I have been able to divide the whole matrix into two parts, need not be equal. So, x, the corresponding value of x, where and those, that is x I, x 1 is a matrix is associated with the beta 1 vector, and x 2 which is matrix is associated with beta 2 vector. So, the sum of squares R for the residuals, which is beta, is called the regression sum of squares due to beta, and obviously, you will have sum of squares coming considering the error part, where the suffix will be capital E. It can be mathematically be expressed as sum of the squares for the betas being equal to beta hat transpose. So, it was basically a vector, it will now become a column vector will become row vector multiplied by x transpose into y. So, all these are y is basically of size n cross 1. Similarly, your x value would be of the size of k into n, because then in that case x transpose y would basically now become k into cross 1 and so on and so forth. So, if you basically do the multiplication accordingly for the matrices. The regression sum of the squares due to beta 1 and beta 2 is already given in the model. So, given the sum of the squares for beta 1 given beta 2 or beta 2 given beta 1 would basically be given by this formula, where sum of the squares of betas minus sum of the squares from coming out from the beta 2 would be the sum of the squares for beta 1 given beta 2, and if you replace 1 and 2 interchange them, it will be exactly the same. That means, sum of the squares of beta 2 given beta 1 would be sum of the squares of beta minus sum of the squares of beta 1. This sum of the squares has r degrees of freedom, it is an extra sum of the squares due to the beta 1 which is happening. So, k, the number of variables which are independent had been divided into r and k minus r. So, whether r is for beta 1 or r is for beta 2 is basically a nomenclature and just a idea method how you are trying to do it. But remember that the matrix multiplication should be commensurate in the sense that the rows and the columns should be such that the matrix multiplication concept stands true. Note that the sum of the squares of beta 1 given beta 2 is the increase in the regression sum of the squares due to the inclusion of the variables x 1, x 2, x 3 till x r. So, that means, in one case I am considering they are to be added to the models, and then what is the increase in the standard errors or the sum of the squares, in another case I am excluding them. So, what is the increase in the sum of the squares. Now, sum of the squares are beta 1 given beta 2 is independent of the mean squares, and thus the null hypothesis where beta 1 is equal to 0 may be tested by the statistics given of f statistics given sum of the squares of beta 1 given beta 2 divided by its degrees of freedom divided by the mean square for the errors. So, the errors also you have the sum of the squares divided by the corresponding degrees of freedom. So, you are taking the ratio of the sum of the squares divided by their degrees of freedom. Similarly, in the denominator you also have the sum of the squares divided by its degrees of freedom, you will give the f statistics under the null hypothesis, and then you will test depending on the value of alpha and the p value whether you basically reject or accept h naught. If f naught, which is under null hypothesis, is greater than that f suffix alpha, alpha again I am repeating is the level of significance, r is the degrees of freedom, n minus p is basically the total degree. So, in f values you basically you try to take the ratios of two samples. So, in this case one sample has a degrees of freedom r and another case the degrees of freedom is n minus p. So, p if you remember Depending on the problem, it can be either k plus 1 or k only, depending on whether you have beta naught yes or no. So that can be changed accordingly. So if f naught is greater than this value, what is this value? I will just circle it. So this one. So here f alpha, again I am repeating the this value. So it is one sided, that is why it is not divided by alpha by 2. So in the other equation, we had basically right hand side and left hand side. Now you are taking only one sided, because it is either greater than or less than. So it is greater than f alpha, r is the degrees of freedom coming from the addition, n minus p is the degrees of freedom which is coming from the total. We reject h naught in concluding that at least one of the parameters in beta 1 is not 0, and consequently at least one of the variables x 1 to x r in capital X 1, which is basically the matrices, contribute significantly to the regression model. Some authors call the test as a partial f test, because you are basically trying to find out the overall effect of r or overall effect of not coming for r. Depending on that, you basically pass a judgment whether you want to accept h naught or reject h naught. Consider the viscosity model again. Suppose that we wish to investigate the contribution of the variables x 2, that is the hypothesis we wish to test is accordingly. Under h naught, beta 2 is 0, under h a or h 1, beta 2 is not equal to 0. So, this will require the extra sum of the squares due to coming from beta 2. So, we can find out the sum of the squares of beta 2 given beta 1 beta naught. So, now you have been able to differentiate and find out the matrix into two parts, one coming from beta 2, one coming from beta 1 and beta naught. So, now from this tables we can find out the sum of the squares of beta 1 beta 2 given beta naught is 44,157, which is called as model sum of the squares in the table. This sum of the tables has 2 degrees of freedom. Depending on that, the reduced model would be like this. So, you have y hat, now it is basically y hat because you are trying to estimate, will be equal to beta naught hat, which is 1652, that is 1652.39, plus beta 1 x 1, where beta 1 hat is equal to 7.6397, plus epsilon would not be there because this is hat, hence we are trying to estimate. So, errors would come accordingly later on. And the regression sum of the squares of these models are given by sum of the squares of r given beta 1 for beta 1 given beta naught, it comes out to be 40,840. So, note that this value is shown in the bottom of the output, and depending on the way you have basically been able to mention them. So, obviously, it can be sum of the squares of beta 2 given beta naught also, depending on how you have been able to so called partition the effects of r and n minus k. So, therefore, SSR of beta 2 given beta 1 and beta naught is 3316.3. So, in this case you have degrees of freedom as 1. This is an increase in the regression sum of the squares that results from adding x 2 to the model already occurred. So, you had x 1, you are now basically adding another variable x 2. So, if you keep adding, what is the sum of the squares change? Now, and whether the linearity of the variables holds, to test h naught, which is beta 2 is equal to 0 versus beta 2 not equal to 0, you can find out the f statistics, that comes out to be 12.39. Note that the mean square of errors, which is basically given in the denominator as 267.604, is used once you find out the values, the f value f statistic based on which you will pass a judgment whether f naught is greater or smaller is 4.67. Now, if you note down these values, so this is basically alpha, this is basically degrees of freedom which is r, and this is basically n minus p. Consider p, p is basically k plus 1 or k depending on how you have been able to mention in the model. Because this partial f test involves only a single regressor, it is equivalent to the t test, because the square of the t random variable with chi degrees consider, so it is written as v, consider this is v degrees of freedom, is an f random variable with 1 and v degrees of freedom accordingly. So, here 1 is r and n minus k is v. To see, note that in the table you can find out h naught as beta naught is equal to 0, and you can test the t values comes out to be 3.55, and you can test using the t statistics, and the values of t statistics are such that is almost equal to f naught. So, depending on whether you want to add 1 or take out 1, they would be equivalent to the t statistics, but if you keep adding more than 1, then obviously the f statistics value would change accordingly. Now, so this initially was about the hypothesis testing. Now, if you want to basically consider the interval estimation of the individual regression coefficients, because the least square estimates beta hat is a linear combination of the observation, it follows that beta hat is basically is normally distributed with mean value of beta as mentioned according to the concept of unbiasedness. And covariance matrix being, if you remember, for the covariance of betas, so it will be k plus 1 into k plus 1 or k cross k matrix, where the principal diagonals are all the standard errors or the square of the standard errors of the betas, and the of the diagonal element are the so called covariances existing between beta j and beta k, or beta I into beta j, where basically I and j change from 1 to k or 1 to k plus 1 depending on how many such variables you have. So, then each of the statistics would basically be that we want to find out the considering the normality holds. So, obviously it would become a very simple test of a z value. So, in the z value what you have when you are converting an x, which is a random variable which is normal, into a z statistics or a standard normal distribution. So, it will be x in the denominator you will have basically the square root of the variance or the standard deviation, and in the numerator you will have basically that random variable minus its expected value. So, if you basically want to find a simile to that what I mentioned, just look at this equation. So, it will be beta hat minus beta j. So, beta hat is the random variable, beta j is basically the expected value divided by square root of sigma square c j j, which is, if you remember, the standardized standard error. So, it is distributed as t distribution with n minus p degrees of freedom, where c j j is the jth element of the matrix x transpose x inverse of that, and sigma square hat is the estimate of the error variance obtained earlier. So, obviously, this 100 minus 1 minus alpha is basically the levels of significance, and based on that, if you basically find out the interval would come like this. So, this is basically the central value, and plus minus for that interval which you want to basically find out. So, the left value would be beta hat minus that t statistics, and on the right hand side it will be plus. Now, note down one thing, it is we are trying to find an interval. So, if it is interval, obviously that value which you have, so it will be alpha by 2 here, alpha by 2 here. So, the whole area inside is basically 1 minus alpha, and n minus p is basically degrees of freedom, n minus k plus 1 or n in the bracket k plus 1 or n minus k would depend on number of variables which you have. So, we can construct a 95%, 90%, 99% confidence interval. Now, beta 1 hat is equal to 7.62, and because sigma square hat is given as 267 and C 11 is given as 1.42 into 10 to the power minus 3, we can find out the confidence interval, where the confidence interval for beta 1 comes out to be in between. At a 95 confidence level, it will come out to be 6.2855 is the left limit, and right limit is basically 8.9570. So, change 95 and the values of corresponding of the left limit and the right limit would change. Depending on that, you can find out the new limits for the confidence interval for betas depending on the level of significance. Prediction of the new response observations. Now, consider a regression model, it can also be used to predict future observations. So, obviously, we have been mentioning time and again, you want to basically find out y hat for the nth plus 1, y hat for the nth plus 2, so on and so forth, find out the error difference for n plus 1 or n plus 2 or n plus 3, and if you want to double check, find out the sum of the errors, they should actually be equal to 0. Okay. So, without repeating, let me come to the problem. A regression model can be used to predict future observations on the response y corresponding to particular values of the regression variables, say x naught 1, x naught 2, so on and so forth in x naught k. So, that means you are taking the first, second, third, fourth is the kth variable and their responses, say for example, for the nth plus 1. Now, in this case you will basically write x naught transpose as very simply mentioned is now basically either a scalar vector or is basically a row vector or a column vector, where the first element remains as 1 because we are considering beta naught is there. So, hence a point estimate of the future prediction model would be found out, where we multiply, if you remember correctly, we will multiply what, beta naught hat plus beta 1 hat into x n plus 1, which is given as x 0 1 here, plus beta 2 hat into x 2's x 2, which is the random variable, its nth plus 1 value, which is given as x naught 2, plus dot dot till the last value, which will basically be beta k hat multiplied by x kth values and its n plus 1 reading, which here is given as x naught k. So, if you want to basically predict a person 100 minus 1 minus alpha, which is the level of confidence which you have, percent prediction interval for this future observations, you can find out that it will basically be y naught. Y naught is basically the without the hat is basically y suffix n plus 1 reading. So, its left limit and right limit would basically be comprised of the values which you have for the using the t statistics, and you can utilize that to find out that how the interval, depending on the level of confidence you have, how the interval will change. So, if you change alpha, obviously the intervals will increase or decrease depending on how you have considered that. In predicting new observations and in estimating the mean response to a given point set of values, which is x naught 1, x naught 2, x naught 3 till x naught k, we must be careful about extrapolating beyond the region containing the original observation, because if you remember, and they would definitely be increase or decrease of the variance and increase and decrease on the trends, so on and so forth. So, how you are going to consider that would be important. We must be careful about extrapolating beyond the region containing the original observations. It is very possible that a model that fits well in the region of the original data will no longer fit well outside the region, because as I mentioned for those points, depending on change in the trend, change in the seasonality, or change in, say for example, pressure, for these examples, change in the viscosity, change in the pressure, change in the flow rate, change in the temperature and humidity, and so on and so forth. So, the prediction interval would have many useful applications. One of those is the conformation experiment following a factorial or fractional factorial experiment. In a conformation experiment, we are usually testing the model developed from original experiment to determine if our interpretations were correct. So, given a in sample and out sample, we will first test our model for the in sample and then try to utilize that model for the out sample and find out the robustness of our model. Often we will do this by using the model to predict the response at some point of time of interest at the design space, and then comparing the predicted response with an actual observations, or it can be a useful measure for the confirmation, so as to see if the new observation falls within that confidence interval, such that we are quite confident that the model or the predicted values of the x's, y's and whatever model we have proposed is right. So, with this I will end the 39th lecture and continue some discussion in the 40th one, and then wrap up this course in the end of the 40th lecture. Thank you very much for your attention. Have a nice day.